Hey there, and welcome back to How'd You Get That? Today we are taking a look at this problem. What is the area under the curve defined by f of r is equal to 0.27 over r squared, evaluated from 0.02 to 0.05? Let's just jump right into it. First of all, when we see the phrase area under the curve, that should make us think of integration. Integration is finding the area under a curve defined by the integrand evaluated from endpoints. And we basically have all we need to solve this problem then. So we need to set up our integration. So the area under the curve is equal to the integral from 0.02 to 0.05 of f of r dr. Now, you'll see we're using a somewhat different variable of integration here, r instead of x or t, but that doesn't really matter. Our function f is in terms of r, and our variable of integration is also r, so they work together nicely. Replacing our definition of f of r into this function, we get the area is equal to the integral from 0.02 to 0.05 of 0.27 over r squared dr. Now I can use various properties and rules to solve this. For instance, I can take the 0.27 factor outside the whole integral, because that's a constant factor. And I'm going to rewrite 1 over r squared as r to the negative 2 power, so that I can use the power rule. So my area is now equal to 0.27 times the integral from 0.02 to 0.05 of r to the negative 2 power dr. Now we can evaluate this integral using the power rule. The power rule says I'm going to add 1 to my exponent to make this now negative 1, and then I'm going to divide the whole function by that new power, so dividing by negative 1. But dividing by negative 1 is the same thing as multiplying by negative 1, so this now gives me that the area under the curve is equal to negative 0.27 times r to the negative 1 power, evaluated from 0.02 to 0.05. Now, when I say evaluated from 0.02 to 0.05, what I want to do is I want to plug those values of r into this new function. And when I do that, I'm going to subtract them from each other. I'm going to find the difference, the final value minus the initial value. If you recall, this is essentially what the fundamental theorem of calculus says we must do. So that means that the area under this curve is simply negative 0.27 times 0.05 to the negative 1 power minus negative 0.27 times 0.02 to the negative 1 power. I'm plugging in 0.05 and 0.02 into the function at 2 different points and subtracting those outputs from each other. Now all we need to do is do a little bit of algebra and simplify this problem down. I can take the reciprocal of 0.05 and the reciprocal of 0.02 and then multiply each of those by negative 0.27, and I finally arrive at my final answer. The area under the curve is equal to 8.1 units. So why this function? Well, it turns out that this function was generated in this way. The function f of r is equivalent to the force function generated by 2 particles in an electrical field where one charge has a charge of 3 microcoulombs and the other particle has a charge of 10 microcoulombs. By doing this integration, I'm actually finding the change in the potential energy of this system. And what we evaluated at our endpoints is what is the potential energy lost as these particles move from a position of 0.02 meters apart to 0.05 meters apart. Interestingly, the force function is proportional to 1 over the distance squared, r squared, whereas the potential energy function is proportional to 1 over r. And for these kinds of forces, called central forces, like gravity is a central force, and the electrostatic force, the Coulomb force, is a central force, this pattern will hold. If you have any questions, leave them in the comments below, along with any suggestions for what you'd like to see on future episodes of How'd You Get That? Hit that like button, subscribe, and hit that notification bell so you never miss another math, physics, or problem-solving tutorial. Thanks so much for watching, and I'll see ya in the next problem.